thank you very much for the invitation. It was a very good reason for me to go into what is web science actually. I'll come back to that. First, I want to explain a little bit how me, being a lawyer and a philosopher, is going to speak on the invitation of the Web Science Institute. I find that law and computer science have something very important in common. Actually, I am appointed at a law and criminology faculty, which is my home territory, but also in a computer science department at another university, the science faculty, where I teach law to computer scientists. And I find that, just like lawyers, computer scientists have a sense of architecture. And I think architecture is what brings law and computer science together, and maybe also web science or some of the questions that web science is struggling with. If I tell to my law students that if you change something here in the multidimensional system that is law, that if you change something here, that it ripples through that system and will have effects everywhere, they look at me like, what are you trying to say? If I tell that to the computer scientists, they say, yeah, of course. And that makes teaching computer scientists, I must honestly confess, a joy. Now, the other side is the title Interpretation and Prediction was taken from an article by Duncan Watts, who has written a lot about the science of networks. And in this article, and many other scholars on the side of computational social science make the same argument. He's basically saying, look, social science has been looking at interpretation too long. We have to move towards prediction. And one of the points I'm going to try and make is that interpretation and predictions are necessarily, if we want to survive, two sides of the same coin. And we have to see their interrelation. Now, for a lawyer, this is obvious. If I want to interpret a piece of law, that means I want to predict what the court will say is the legal effect of a certain state or a certain action. So what the law does, to put it very simply, is attach legal effect to certain legal conditions. And these legal effects have real consequences. It means either you go to jail or you don't. Now, this coming together of interpretation and prediction is very important, and I'm going to come back to that. I'm going to talk a lot about machine learning and about artificial intelligence, and I want to start with some concepts that have been offered by some people who are working in this field. Federico Capizza, I think he's a very interesting scholar. He speaks of oracular AI, artificial intelligence, and I quoted him where he says, like any oracle, we describe it as any decision aid capable of providing its user with very accurate responses, for instance, no more than 1 error out of 20, and little or no explanation for that advice. This is often termed the interpretability problem in machine learning. That has given rise to a whole series of articles by lawyers and computer scientists writing together on whether we can resolve this interpretability problem. For instance, because the upcoming General Data Protection Regulation requires that if decisions are taken based on such machine learning and they have a real effect on the life of people, they have to be explainable. So that was the interpretability part. Of course, that also has a predictive part. One of the points I'm going to try and make is that whatever the huge expectations of artificial intelligence and certain types of machine learning at this moment, whatever the fact that it is actually now implemented and having a real effect on our lives, when it becomes really important, maybe it doesn't really work as well as some people say. There is another concept that I want to use, a concept introduced by McQuillan, which is machinic Neoplatonism. Yes, I'll repeat that, machinic Neoplatonism. So he basically describes that most mathematicians are Platonists. So they think, okay, we have the world here, that's very interesting, but reality is the underlying mathematical structure of the world. Yes. What we see is just, a mess. So if we can get to the mathematical reality, we're good. So he's talking about Neoplatonism, where this idea about reality is being transferred to the idea of datafication, which is, of course, when you look at what is done, the computations that are done on data, is very close to this mathematical reality. Now, he puts in front of that the word machinic, because with the type of decisions that computers are now making, and especially if you move towards robotics, the Internet of Things, smart grids, etc., this mathematics is being welded together with machinic consequences, with hardware. Let's put it that way. So it's now becoming even more real. And McMillan, for instance, says, for the data scientist, computation plays the role of the intermediary between the imperfect world of data and the pure function that relates the features to the target. So the idea of much machine learning, maybe all machine learning, is input data, output data with reinforcement learning. You have the output. For instance, the output is a picture of a dog, yes or no. So you feed the machine a lot of pictures, and you want that machine to learn to recognize that what is a dog and what is not a dog. And the machine does that not by coming to understand what is a dog, but by discovering the mathematical function that approximates the operations, the mathematical operations between the input and the output best. So that relationship is called your target function. And what you try as a machine learner is to come as close to your target function as possible. But the real target function is, of course, a pure mathematical function. And here we see one of the famous cartoons that I think you might have probably seen many times now, because it's going viral, about the Internet of Things and all sorts of implications where you see the hardware side and how this is going to impact us. Now, this is related to the fact that we're sort of encountering things. It might be this table. If this table is connected to the other table, to all sorts of other parts of this building, and to a system that reads all its sensing data and then does calculations, that system behind the table might then develop certain thoughts, between inverted comma, about me. It might recognize me, it might calculate my preferences, it might auto-tune the sound to the whole, etc., etc. And I'm often using this slide to show that perhaps the term think here is used in different ways. But I want you, now that you have looked long enough to this cartoon, to answer this question. We take for granted, and actually when you look properly, that's also how the cartoon is meant, that that question is asked, or that remark is made by the machine. But maybe it's more interesting to go fast forward and go to the moment when we are going to ask that or tell that to the machine. And machine might say, ha, your kind of thinking is very poor. I can do it better. I want to talk about 6 things, and we'll go through that. So first of all, Sir Tim Berners-Lee, who was one of the founding fathers of the Web Science Institute, in a keynote at the W3 conference in 2007, he talked about 2 magics of web science. And in brackets, he says magic is things we don't understand yet. I'm going to use another way of talking about magic, but let's for now talk about magic things we don't understand yet. And he raised 2 very interesting questions. First, when does the microscopic interaction between 2 people on the web scale to produce a new macroscopic phenomenon? And I've highlighted when. The question is not why. The question is when. We're not talking interpretation, deep thinking about why this is all happening. We're talking when. We want to be able to predict this. Second, what creative magic is required to identify new microscopic designs that could have positive macroscopic effect? Again, the question is not why and how. It's an engineering question. How can we reconfigure at the bottom level of the web the design, the protocols, whatever, the APIs, whatever, in such a way that the interaction that takes place there, for instance, doesn't lead to filter bubbles, fake news, disturbance of elections, and what have you. I take it that it's these sort of very practical questions, actually, that are at stake, but understood at a more fundamental level. How can you design an environment that does good things? Of course, for a lawyer, the question is who determines what is a positive microscopic effect? And in issue 2-3 of volume 4 of Foundations and Trends in Web Science, I found a wonderful article which takes this question of article. It's more like a book. It takes up this question, it takes it serious and further discusses it. I also found the manifesto for web science at 10 years after the start of Web Science Institute. And that manifesto aims to take a socio-technical perspective, including its mathematical properties, engineering principles, and social impacts. And then we get a discussion about the notion of a prosumer. This notion has been around for quite some time now, and we might start asking whether it isn't naive to think that the individual users are prosumers, if they are not to some extent manipulated into all sorts of supposedly productive behavior. This relates, of course, to personalization, social networks. To what extent are they echo chambers? Of course, the web was first about linking documents, then data, then behaviors, devices, and people. And I see now that in discussions about privacy, some people are beginning to raise the question whether for this particular era of hyperconnectivity combined with computation, we need to articulate a new privacy right, the right not to be linked. Questions about who creates, controls access to data, to behaviors, to inferences, the discussion about the platform economy. Then very practical engagements with a web observatory. The idea, the notion of social machines, so the hybrid between people and the the infrastructure, the design of their environment within which and with which they interact. The idea of code as law, the fact that code restrains us, which also enables us to do things that we couldn't do before. And for me as a lawyer, the question is whether all this code and the whole architecture is still under the rule of law, or if not, if it can be brought under the rule of law. And then there are, of course, these issues of emergence, complexity, networks effect, turbulence, scale, etc., etc. And here again, in the article, that is actually a book, we see a move away from interpretation, a focus on prediction. It says the aim will not just be to understand the emergent phenomena, but rather to develop means, methods, and tools for controlling large-scale phenomena. And there is modesty here, at least partially. So this is about prediction and interpretation. And prediction is, I find in these writings, very much linked up with control. So the idea is, the more you can predict, the better you can control. Then there is modesty, so maybe control is taking it too far. Let's talk about how can we influence. What is influence? How does influence trickle through the system? Of course, Duncan Watts, who I referred to, has done lots of research on this. Now I'm going to say something which may surprise you. I'm going to say that prediction means that you are creating present futures. So you are basically saying, if this and this and that happens, I'm predicting that that will happen in 5 days or 3 years, depending on that. So that is a certain picture of the future. But it's not the future itself, clearly. So I'm calling that present futures. So prediction is about present futures. It's not about the future. It's about present futures. Interpretation, in the sense of meaning and understanding, that means amongst people, in terms of natural language, is something different. It's not about causality, though that certainly plays a role, and or correlation, but it's about how we constitute our shared world. So this is a wall. If we have a bat here, one of these flying animals who don't see very well, but they hear better than us, it will see this wall, but not like we do. It will basically get the echoes back. That means it will not bump into that wall. But to the bat, this is not a wall. It knows nothing about the concept of a wall. Bats don't build university buildings. So it lives in a very different type of environment. Now, by interpreting our environment, we also create that environment. There's very interesting and very relevant literature on the financial markets. How all the predictions that are being automated, modeled, about transactions on the financial markets, how all these predictions basically shape the market that they try to predict. And I hope you understand that the better you predict, the bigger the chance that your prediction won't come true. Because once that prediction is there, people are going to respond to it. So everything is going to be different. So interpretation is anticipation. We're not interpreting because we are sitting with our back to reality. We are interpreting because that is how we learn the kind of world we are in. A world that is largely constituted for human beings by language. I mean, this wall is not constituted by language in the sense it's made of bricks. I'm aware of that, though this is hard. I'm not sure this is bricks, actually. But the fact that it's a wall and what it means to be a wall or to have a wall, that is something else. So I'm going to turn our intuition around and say that prediction is about the present. Prediction doesn't give you the future. It's about creating present futures. Interpretation, however, is always an anticipation. You're trying to interpret things so that you have a better idea of how your environment is going to respond to you if you do something. I'm going again back to the article that is a book. Here it says, the problem is sharpened by the desideratum, the wish that programming the social computer must be achievable from within the social computer. And then it says the methodology of web science should output policy for governments and large organizations, but it will also democratize control by allowing people to develop social machines to achieve their own smaller scale, local, idiosyncratic purposes. I'm going to make a change. I'm going to make an amendment. So it said but. It said but, as if there is government and large organizations and we have to cater to them and we have to help them to survive in a competitive world or whatever. And then there is these folks on the ground and, you know, but they also have to do something. I think that the government, for instance, is there for us. We're not there for the government. So if we're going to output policy for governments, that policy should be articulated in such a way that it democratizes control. What companies can do is determined by private law and to some extent by public law, administrative law, international law, human rights law. The market in which companies operate is constructed not by God, not even by Adam Smith. It's constructed by private law, contract law, the freedom to contract, ownership, the freedom to dispose of your property. So we should create the incentive structure that allows companies to make a profit and to hire people. To do that also in such a way that it democratizes control by allowing people, etc. So I want the opposition out here. Now let's move on to what I mean with magical thinking. And I'm going to move back to this concept of machinic Neoplatonism. I'm going to give you an example of a question that Stephen Hawking asked Mark Zuckerberg 2015. He asked him, what would you really like to know? What are you curious about? What makes you tick? And then Mark Zuckerberg confessed himself to be a machinic Neoplatonist. He didn't know that and he still doesn't, but he says, I'm also curious about whether there's a fundamental mathematical law underlying human relationships that governs the balance of who and what we all care about. And then he says, I bet there is. So that's what he's after. So the idea is that what we do, how we communicate with each other, what we care about, what concerns us, is basically determined by a mathematical law, a very fundamental mathematical law. And that suggests that whoever gets, let's say, her finger on that law, wow, that's going to be a very powerful person. Thinking machine learning, thinking the main paradigm, the more data you have, the better output you have. Facebook is in a marvelous position to get its hand on that mathematical law. At least I think that's what Zuckerberg hopes. Now, when I think of magical thinking, I think of something that is I found a wonderful and brief and adequate description in Wikipedia. So actually philosophers and lawyers are not allowed to cite Wikipedia, but I'm very undisciplined, so I dare. It says it's a term used in anthropology and in psychology, denoting the fallacious attribution of causal relationships between actions and events. So in anthropology, the attribution of causality between entities grouped together. So the idea is that primitive tribes have seen 10 times that it rains when they have scratched behind their ear, and they say, well, that must be it. Let's group together and do this, and it'll probably rain again. That's a very boring and incorrect presentation of how primitive society works. I don't think it works like that at all, and lots have been written about it. But the idea that sometimes people have a mistaken idea about causality goes for all societies. In psychology, the idea is that sometimes people think that if they do something, that it causes, for instance, bad things. So if there is this bottle and I depict it as a person that I totally dislike and I put nails in that bottle, I believe that that person is now going to suffer. We call that magical thinking. In both cases, the belief can cause a person to experience fear, which seemingly is not rationally justifiable to an observer who is outside that belief system, of performing certain acts or having certain thoughts because of an assumed correlation between doing so and threatening calamities. Wow, that's a horrible sentence. Let's keep it simple. I'm going to move on to magical thinking in the current political economy of the on-life world. With on-life world, I mean the fact that the difference between online and offline is becoming increasingly artificial. So we think, when you sit behind your screen, you go online, and when you turn around, you're back offline. But with the coming of the Internet of Things and with the range of decisions that are being taken by all types of decision systems, software, that distinction may be very misleading. So with a group of philosophers, neuroscientists, and computer scientists, we have coined this the on-life world. So what sort of magical thinking is present in that on-life world? Well, I would say like this: it's a mistaken belief in causal influences and or predictive accuracy based on illusionary, wishful or fearful thinking about the nature of the world. So for me, magic is not something that you don't know. Magical thinking is that you have the illusion that where there is basically uncertainty, you can create certainty. That means that to get rid of magical thinking, we have to face the temporality of human interaction. What do I mean with that? Well, I mean with that if you do machine learning, for instance, you're always doing the machine learning on a training set. Then you are maybe working with a validation set, test set, and it works. And let's say you do it iteratively until it approximates and you say, okay, this is great. But the minute you begin to apply what you have found on new data, which were not yet there when you were training your algorithms, things may have shifted. And there is nothing you can ever do about that, however mathematically correct you have been. There is a famous computer scientist, mathematician, David Wolpert, who actually proved that mathematically, Wolpert's theorem. That is connected with the fact that there is something called time. So uncertainty is inherent in our temporal existence. Now this uncertainty also creates possibilities. If you would know at this moment everything that was going to happen to you till the day you die, which also means when you're going to die, would you still want to live? Would you have any freedom left? No, you wouldn't. So this uncertainty is somehow connected with freedom, not in an obvious way, because freedom may sound like you can still control things, and that's not obvious. So the question that is at stake here, which is a question that is crucial to machine learning, is the future like the past? All machine learning is based on an assumption that the future is, to some extent, like the past. The question then is this a question about causality, the laws of nature, or about logical necessity, mathematics? And are we talking about how the present futures that I talked about co-determine the future present? That means they are actually performative. Now, I have articulated this, actually not this year, but last year, in this way. And actually, this is the most crucial slide of today's lecture. I could stop after that because it basically says it all, but I will go on a bit. But this is the core. Since the present futures co-determine the future present, predictions basically enlarge the probability space we face. Probability space is also a core concept in machine learning. So predictions do not reduce uncertainty, but they enlarge uncertainty and possibility. Now the interesting question here, and that is also a political question, but also a design question, an engineering question, is the question about the distribution of the uncertainty and the possibility. Who gets how much of which? Who get all the uncertainty and who get possibility? The question is not obvious, the answer is not obvious. I have presented this to a whole, all my colleagues in the science faculty in Nijmegen. It relates to Wolpert's no free lunch theorem. I think it is something we need to talk about, we need to face. I think it is something on the cusp of politics, design, architecture, computer science, and especially the implementation of all sorts of AI decision systems, especially the oracular ones. So this is inspired by the work of Elena Esposito, who is very much inspired by German philosopher Luhmann and German philosopher Koselleck. And Esposito wrote a book, The Future of Futures, which I would abbreviate to this, what I said, the present futures, that's plural. We're usually making more predictions than one. Co-determine the future present. There is only one future present. That means we have to be careful. The more we predict, the less predictable our world. Why? Because people are going to respond to the predictions. And we don't know what they'll do. Of course we'll try to predict that. to the n dimensionality, but we don't know. Fundamentally, we don't know. And the more complex we make the prediction of how people will respond to our prediction, the more unpredictability we generate. Now, this is related to something that in sociology has been called double contingency. That is actually core to prediction and interpretation. So life, that is organisms that have to survive, that have to continuously profile their environment to know if they're moving, whether they're bumping into something, or to know when they're talking, whether other people will actually understand them. That means that an organism is always continuously anticipating the behavior of its environment. Now that relates to causality. But when you're talking about human beings, there's something new. We are all the time trying to anticipate how others anticipate us. When I'm talking, when I'm using words, when I'm talking to you now, I'm doing that because I anticipate that the vocabulary that I use, I know it may be unfamiliar, but I hope that the way I talk, that you will understand. So I'm continuously working hard also while preparing, but also when standing here. And this is related to the idea of the first person in a grammatical sense. And I always try to explain that this way. Imagine if I have a small child, I think it's about 1.5 years old, and I tell that child, you are Kieran, I am Mireille. And the child listens to me and says, yes, child here, you are Kieran, I am Mireille. And I say, no, I am Mireille, you are Kieran. And the child says, yeah, you are Kieran, I am Mireille. The child is imitating me. It takes some weeks before the child realizes that I am you to her, and she is I to herself, and you to me. The child has to decenter and look back at itself from another position. Now that's the birth of the first person grammar. And though I have 2 cats, they're extremely smart and intelligent, but they don't make this turn. So they're smart, they are anticipating their environment, blah, blah, etc. I'm absolutely convinced they have some sense of causality even, which is not obvious, but they don't use language. They don't make this turnaround. This also means that by speaking to each other, we often do things. Speech act theory. If the civil servant has a man and a woman, or depending on the jurisdiction, 2 men or 2 women, in front of her, and she declares those 2 people married, she's not describing something. Once she writes that down in the public register, if one of them, depending again on the jurisdiction, but in the Netherlands, if one of them makes debts, the assets of the other person are liable for those debts. That's a real effect. And that effect is attached the minute that civil servant says, you are man and wife. Speech act theory calls that the performativity of certain language utterances. Now, it's very interesting to see that when you're talking about machine learning and prediction, machine learning has this term performance metric. There is no machine learning if there is no performance metric. Otherwise, you can't measure whether the machine learns. Otherwise, the machine cannot evaluate whether it's learning. And that means it cannot learn. Now, performance metric is something very different from the performativity of human action. Let's have a look at what machine learning does. An example, take an algorithm that uses EHR data to predict which emergency department patients are at high risk for stroke. It would learn to diagnose stroke by churning through large sets of routinely collected data that are already collected anyway. Critically, all these data are the product of human decisions. A patient's decision to seek care, a doctor's decision to order a test, a diagnostician's decision to call the condition a stroke. So rather than predicting the biological phenomenon of cerebral ischemia, the algorithm predicts the chain of human decisions leading to the coding of stroke. There's nothing wrong with that. Unless we mistake the prediction for something entirely different. Now let's quote some people on what I call magical thinking. For instance, about reinforcement learning. In this case, what I would call machine learning echo chambers. Rodney Brook is a famous roboticist, and on his blog he's written a story about machine learning explained. And at the end of his explanation, he does a little postscript, and he writes about what machine learners, researchers in machine learning actually do. Well, they write papers. They write papers and they present them at conferences. And then he says the papers and conferences fall in two different categories. One is mathematical results showing that yet another slight variation of technique is optimal under some carefully constrained definition of optimality. The second type of paper takes a well-known learning algorithm and some new problem area, designs the mapping from the problem to a data representation, and show the results of how well that problem area can be learned. I would like to call that, and if we have time at the end, get your responses, because I'm sure there are machine learners here. I would like to call this an echo chamber. So you do all sorts of research in a very narrow, not a laboratory, this is not empirical, but in a very constrained situation where you begin with, let's say, 4 different assumptions where everybody agrees that they do not apply. But if you do not take these assumptions, you cannot calculate, you cannot do your machine learning. Now let's go a step further and talk about magical thinking in terms of deep learning. This is an interview with Geoffrey Hinton, one of the most famous people who actually initiated and further developed deep learning. It goes a long way back. And he explains that this is a matter of back propagation. And he says, yes, it has a core role in AI's future. But then Hinton himself says that to push materially ahead, to really get on, entirely new methods will probably have to be invented. Max Planck said science progresses one funeral at a time. The future depends on some graduate student who is deeply suspicious of everything I have said. And this is interesting because everybody is now saying that deep learning is fantastic and it's general intelligence, and soon we will have singularity and superintelligence. Well, this is what Geoffrey Hinton says. How it works: in back propagation, labels or weight are used to represent a photo or a voice within a brain-like neural layer. The weights are adjusted and readjusted layer by layer until the network can perform an intelligent function with the fewest possible errors. This is what I was talking about. So you're trying to come from input data to a specific output. And this is all done by means of mathematical functions. And you readjust all the variables that are at play until you approximate the closest the relationship between input and output by testing and retesting. But Hinton suggested that to get to where neural networks are able to become intelligent on their own, what is known as unsupervised learning is necessary. I suspect that means getting rid of back propagation. I don't think that's how the brain works. We clearly don't need all the labeled data. Another example of what machine learning does. Here we have an investigation about the use of medical data. And these medical data have been prepared by doctors or caretakers. In this case, I think it was about radiologists. So you have radiologists making a diagnosis based on images. You feed these images to a machine. You give the machine the diagnosis of the experts, and you repeat that, to put it very simply, until the machine has found the mathematical function between the input data and the output data. But this article by Kabitsa is about the data set that is used, the input data. And when you look at the left 2 points, A and B, he says on the left side, you see all the dots together. The experts agree. They all say this is appendicitis, what we see here. The second point, B, you have variability between the experts. That's called inter-rater rating. So that's a that's a variable. So if they don't agree, if one says it's appendicitis and the other one says something else and the third one again something else, and they don't really agree, then you get that swarm. That's about reliability. Now let's move to validity. You don't only want to have experts agreeing, you also want to be able to teach the machine. You want to have what is actually the truth. In machine learning terms, that's called the ground truth. First I thought this was about like a coffee mill, that you had to ground something and then you got out the truth. But I understand it is the truth on the ground. So the people who are actually working with things, they know the truth. So you go back to them, you ask them, and then you have the ground truth. So under C, you see that the ground truth, that's in the middle, makes the agreement between the experts, the swarm, a bit off-key. So if that's your ground truth, problem. If D is your ground proof, you don't have that problem. Now, of course, my question is, if the experts are somewhere, how did you get the ground truth? Was there a way around the experts to get the ground truth? How did you calculate that? Etc., etc. Well, this is connected with what some people have called the McNamara fallacy. I'm sure that some of you remember the Vietnam War and McNamara's idea that you could predict the outcome of the Vietnam War by calculating dead bodies, etc. I'm now quoting Daniel Yankelowicz, if I'm pronouncing his name right. And he says, the first step is to measure whatever can easily be measured. This is okay as far as it goes. The second step is to disregard that which can't be easily measured or to give it an arbitrary quantitative value. Think a consultant that is hired to come up with a certain software project, who is trying to shape order into things. This is artificial and misleading. The third step is to presume that what can't be measured easily really isn't important. This is blindness. The fourth step is to say that what can't be easily measured doesn't really exist. This is suicide. Now, I'm sure that everybody who looks at these steps says, yeah, of course, who would ever think otherwise? Well, I'm afraid that when you look at the incentive structure for companies, governments, who are outsourcing much of the machine learning applications and who are asking companies, consultants, whatever, who have to survive in a market and who know that if they say, we can't do anything with this data, you need to get those data, and the company will say, yeah, but that's going to cost a lot of money, or that's not possible because of privacy reasons. So there is an incentive to then say, oh, well, you know, we'll just do it with the data that we can get our hands on. Then we're in step 2. And the other steps will necessarily follow. And I'm sure you've all read about how governments sometimes push for risk analysis, where there's a lot of uncertainty, and then the government says, yeah, but, you know, we can't calculate with uncertainty, so just give me a value that's reasonable. Okay, now I'm going to introduce not a solution, but a way to cope with this. And I've called this agonistic machine learning. The term agonistic comes from two scholars, Chantal Mouffe, who is a political theorist who works on democratic theory, and Arie Rip, he works on constructive technology assessment. Chantal Mouffe says the big challenge of politics is not to assume that we're going to deliberate and reach a consensus, a rational consensus. You cannot assume that. So what we need is agonism, not antagonism. People who, anytime you say A, they say B, just for being antagonistic. That's not interesting. Arie Rip basically says the same about when you want to test new technologies, the introduction of new technologies. Make sure that you have both domain experts and the people often called users that are going to suffer the consequences, that are going to work with this technology. And be sure that if you have involved them, you'll get far more robust knowledge. Now, here comes the rule of law. Contestation is at the heart of the rule of law. Without the testability of machine learning systems, you cannot contest their output. That means we might have to restrict the employment of Irregular AI, something that is not testable. And that also may mean that we have to acknowledge that the idea of purpose limitation, which is a core principle of data protection law, actually aligns with the methodological integrity of informatics, of computer science, of machine learning. Very quickly, to go into the article from Duncan Watts on interpretation and prediction. Let's take Duncan Watts as an example of what agonistic machine learning could look like. Because though he takes the attention away from interpretation, he wants to move towards prediction, I think he does that in a very interesting way. He discriminates between exploratory machine learning and confirmatory machine learning. And then he says, with exploratory machine learning, researchers should be free to study different tasks. And tasks is a very specific technical term in machine learning. There is no machine that is ever going to learn anything if you do not code a task. Describe in machine-readable terms the task that determine what it has to do. To study different tasks, fit multiple models, try various exclusion roles, and test on multiple performance metric. The output of a machine learning application, of course, entirely depends on your performance metric. What are you measuring? Of what do you say, well, this means it's actually learned something? Where's the threshold? How do you design your performance metric? And when reporting their findings, they should transparently declare their full sequence of design choices to avoid creating a false impression of having confirmed a hypothesis rather than simply having generated one. That's a very different thing. And report performance in terms of multiple metrics to avoid creating a false appearance of accuracy. So you're basically asking of machine learners to play with the data, to try out different training sets with the same algorithm, different algorithms with the same training sets. Then he says, when it's about confirmatory machine learning, so when you're basically claiming that you now have an algorithm that is actually very good, that can be brought out into the real world. He says you should require machine learners to pre-register their research designs, including data pre-processing choices. How did you cleanse your data? Where did you get them? How did you curate them? Model specifications, evaluation metrics, and out-of-sample predictions in a public forum such as the Open Science Framework. I think that's an extremely interesting and important suggestion. It doesn't necessarily make these algorithms replicable. That depends on a lot of other things. But it makes them testable. In a mathematical sense, for instance, and potentially, partly also in an empirical sense. So here's my last slide. And I'm going to try and wrap up, and I'm sure I've confused you by going in different directions. For me, it's all very coherent, but I'm not sure that's for everybody. So I'm going to try and move from magical thinking to rigorous speculation. And this means that magical thinking is to suggest that we can do better than rigorous speculation. I don't think we can do better. So it is better to recognize that. We can speculate, the future is not here, so we can speculate, and we better do that rigorously. But as soon as people begin to suggest that we can do better than that, you better count your fingers. So I think it is very important to rethink interpretation and prediction in terms of their interaction. So to stop opposing them. Speculation implies that you take seriously the uncertainty that is generated by prediction. So the intuitive thing is, if I predict something, I reduce uncertainty. That may be true under constrained conditions, but certainly in machine learning and its application, it is not. It will generate uncertainty. And it will generate complexity and turbulence, etc. Now, speculation is one thing, but I'm not talking about just speculation. I can go and speculate on Sunday afternoon after having a lot to drink. We're not looking for that. We're looking for rigorous speculation. And for that, I think we need agonistic machine learning. And that means getting machine learning out of its echo chambers. So on the one hand, the academics, the scientists who are doing machine learning, my colleagues, I'm appointed at a computer science department, who are very serious and they're completely aware of their echo chamber, of all the assumptions they make that don't hold. So more excellent machine learners should get out of their echo chamber and dare to admit, okay, these assumptions are never going to apply in real life. Let's really try to do something, make assumptions that do apply, even if that makes our task incredibly more difficult. Of course, I also hope that all the consultants who take the results from academic research and cut out the assumptions, pretend there are no assumptions, and just present the end result as if it's, well, some sort of truth. That's even more dangerous. But for consultants, it's far more difficult because they have to function in a market. There is an incentive structure that makes it more difficult. So that requires rethinking legislation, recreating a market that is more conducive to a better architecture for machine learning. It also requires agonistic interaction between machine learners, domain experts, and those subject to its jurisdictions. When you look at the, like lawyers think they create the architecture of society, or that they maintain the architecture of society. I think we are now in an era where that's basically computer scientists. And they have to start talking. And it's very important for agonistic machine learning that they talk to the people who are under the jurisdiction of these systems. Then one outlier, I didn't talk about privacy because these issues are too easily reduced to privacy issues, and I think privacy is just one issue. But I think besides the idea of not wanting to be linked, there is another way of looking at privacy, which is becoming more urgent every day. And that is privacy as the protection of our incomputable artificial nature. I think our nature is very artificial. Like my cat has a nature which is to a very large extent determined by an interesting combination of nature and nurture, so its bodily, its biological existence and the environment in which it comes. But it's not comparable to what we have constructed with language, a whole world, meaning. Now, I think that the core of who we are is not computable. Is not computable. And that has to be protected somehow. And, okay, part of that is the right not to be profiled or linked. But another part of that, and that's very important, is to say, okay, I am not computable in the sense that you can define me entirely with your computations. That's not possible. One way to protect yourself against that is to say, I can be correlated, my data can be correlated in different ways. Agonistic machine learning. You can datify me in all sorts of different ways. And I have a right to that. So if you say that I am somebody who's not paying her bills, I want to see on what data your algorithm was trained. I want an explanation. And I want the right to even fit your profile, but to be the person who changes and does pay her bills from today. That means the right to contest any particular way of being linked or profiled. I wouldn't believe it, but this is the end. And here, some advertising for, yeah.